So, Gary, the floor is yours.
Thank you, Kevin, and good afternoon to everyone on the East Coast and center of the country, and good morning to those of you further west. We're going to talk about the Conceptual Foundations portion in the next half hour here. And what we want to do is, I'm trying to actually advance my slides. There we go. There are 5 conceptual foundations, and I'm not going to read all this. You can read that yourself. But the first one, basically, knowledge of spatial relationships, and we're going to look briefly at each of these in the next half hour. Second one, knowledge of spatial data models. Thirdly, understanding of some of the conceptual foundations on which GIS are based. Fourth, knowledge of the Earth's geometry. And fifth, knowledge of some georeferencing systems. So let's go ahead and get started. GIS is all about spatial relationships. And while we may think of up and down and left and right, spatial relationships are much more complex if we are to represent them in a meaningful way. What we have here is a road and 2 houses. What is the distance between the houses? That would seem to be a pretty easy question. But let's overlay some contours, which are discussed more in the cartography and visualization section, onto our simple map here. We see now that there's some relief involved, but yet without some more information, we still cannot talk intelligently about the distance between the houses. So here we've added some index contour labels, and now we can start to get a sense of what the distances might be. If we look at a cross-sectional view of our contour map from the left, and noting those index contours, we see a 740, a 730, and then a 720 down towards the bottom. Looking at this contour, from the cross-sectional from the left, we see the house up on top. We see the house on the right. And all of a sudden, now we can start talking about distances. That we could say, well, a distance between the houses is a direct distance would be the slope distance. But we may be more concerned about a horizontal distance or vertical difference. So we can see that just simply talking about distances is really not meaningful until we start looking at these more complex relationships. So maybe in its simplest form, direction is simply just an orientation to north. Every map has to demonstrate how it's oriented relative to north. We normally think of north simply as being up, but some situations or some client requirements may require otherwise. North may be to the right or down or to the left. Just as important as orientation, though, are directional relationships. If the house at the bottom of the hill has solar panels on its roof, will the house at the top of the hill block the sunlight from reaching those panels? Well, that's going to depend on all sorts of factors, including the latitude at which these houses exist, the horizontal and vertical distances between the houses, the height of the houses, which direction north is, and how the houses are oriented to each other, what direction they lie from each other. If north is to the left, and the houses are in the northern hemisphere, the sun will be to our right, and there really shouldn't be any issue. But if north is to the right and the sun is to our left, especially the higher the latitude that we go, we will need to carefully analyze the directional as well as the horizontal and vertical relationships, because we can see here that in the wintertime, if we are far up north, the house on the right may have its solar panels blocked from the sun. So we need to start understanding these relationships if we're going to make a determination as to that what condition we're going to be into, maybe how high the houses can be built or how high they need to be built, that sort of thing. You can now we can just touch on topology, right? Topology represents the spatial relationships, and these are ubiquitous in GIS, whether in the mapping of parcels or soil types or impervious surfaces, or a multitude of other potential features. There's an expectation that for each type of feature, each discrete area will be independent of its neighbor with no overlaps or gaps. Otherwise, any analysis becomes suspect. For example, here, the total area of the entire 4 parcels is suspect because the areas of the parcels the areas of the parcels individually, I should say, because of an apparent overlap between parcels 3 and parcel 4. The overlap may in fact exist on the ground, but either way the system must know what to do with it if an area analysis is to be meaningful. Shall it be its own parcel? Or how do we show, in other words, the overlap, maybe it should be its own parcel. How do we show that it's not merely a mapping error? Now let's overlay soils onto the top of our map. Here, of course, we will have an overlap between soil types and parcels, but there should not be any overlap between the soil types themselves. Each must fit with its neighboring soil type. And then we can do analyses and determine how much of a particular soil type exists on what parcels. And this plays into tax assessments, particularly in farm areas. Topology. Let's look now at these some of the standard spatial data models, and we're going to look at specifically at vector, raster, and object-oriented models. It's important to understand what each represents and the advantages and disadvantages of each one. Raster data are comprised of discrete pixels. From a normal perspective, a raster image may look crisp and clean, as in this one. Everything looks fine here. But as we zoom in, we find that the image is obviously formed by many pixels, and we can start seeing the pixelization of the image. And when we zoom in far enough, we really see what's going on, and the image becomes completely unusable. So this is an example of what we run into with raster data. When we talk about vector data, this is essentially a mathematically defined path that represents locations and shapes. Here we can see how an image might be represented as a combination of mathematically defined vectors versus a series of pixels, which is how it might appear in a raster image. I think this is a pretty good example of the type of thing we're talking about here. When vector data are zoomed in upon, there is no loss of resolution. The mathematical definition is adjusted to the scale, but the raster image starts becoming clearly pixelated, as we have in this case here. The relational or entity relationship models provide for database entities that have certain attributes on which relationships can be built. Entities of a certain class or a type, for example, person and city. And then entities have associated elements of data, or what we might call attributes. So a person has an age, a city has a population. And then those entities have relationships between and amongst each other. How many people of a certain age live in a city having a certain population? And this is where relationships can be built, and we can really start doing some meaningful analysis of our data. In object-oriented database models, they represent a very much of a leap forward over the traditional georelational data models, because the spatial and attribute data are essentially one and the same and are actually stored in the same system. As such, the entities are objects then that can have a variety of properties and behaviors and relationships, and those objects can be of differing complexities and contain different features. And the user then has the ability to define the relationships and set the rules. So there are, the object-oriented model is a great leap forward compared to the previous models. So let's go on. Our third item under the conceptual foundations is understanding the foundations on which GIS are based. And this includes some of the problems that we face in real life. For example, change over time. This can be a critical issue in many applications. Right, so we know that cities expand typically, in most cases, kind of in an uneven way. Areas get annexed and subdivisions get built and that sort of thing. And then roads get built, and they're built usually in some systematic way, so they make sense and they tie in together. But then we throw vehicles on top of those, and we know vehicles move in an illogical way. Right? We don't know how they're going to go. In addition, we have accidents and we have construction going on, which may alter what would otherwise be a route that could be anticipated with some level of confidence. And if we move into things like diseases, we know that those can migrate completely erratically. And yet, historically, we know that time is just as important as, the time from a historical standpoint is just as important, maybe more important than what's going on contemporaneously. And then even when we do understand these contexts, something that we have to recognize and account for and actually make sure that users understand is that there is imprecision in everything that we represent in a GIS. It may be small or it may be large. It depends on exactly what features are involved and what the source of that information was. And in some cases, we may be representing very imprecise information overlaid with very precise information. And then we may be kind of inadvertently fooling ourselves and our users by implying precisions that are not there. So it is a very important issue to understand this. The fourth conceptual foundation is a knowledge of Earth geometry. And there are a number of things that we need to recognize and account for as we address this particular issue. One is, of course, the Earth is not a perfect sphere. It is somewhat of an ellipsoid, but it's not a perfect ellipsoid either. It has an irregular surface. And so we end up needing mathematical models to represent what it is and to be able to accurately show features on top of it. So it becomes important then as part of what we need to know in our use of a GIS or in building GIS is how are these models developed? What are they based on? Right? The Clark's ellipsoid, I think it was 1866, and more and more precision in the mathematical models that we have today. But what exactly do they represent? And how accurate, in fact, are they when we're trying to represent this irregular surface? There are inherent flaws in every model, And so we have to understand there in some applications, a particular model may be better than for use in that application, using that application than in other applications. So it's a very important thing. We can look simply at the Earth's geometry. If the Earth were a perfect sphere, then many, if not most of our problems would disappear. But in fact, it's not. And we need to understand what its shape actually is in order to use it to best advantage, or be able to represent it to best advantage. There are innumerable projections of the Earth's surface, and every one of them serves a purpose, and some of them hold certain features fixed, and other features, other kind of elements of the geometry have to give. This happens to be the Robinson projection here. So we can look at this fifth foundation, and this is knowledge of georeferencing systems, which would include coordinate systems and different spatial relationships, right? There are a lot of different reference systems, datums, projections, and coordinate systems that we can use to represent locations and to show the positions of features on the Earth. And we need to understand what the purpose of each is, so that we can best represent, and just as importantly, and perhaps more importantly, not misrepresent the information that we are trying to convey. Just in this view here, we can see what appears to be on the right, a Robinson projection, and then we have more or less a globe on the left. Well, how do we take that information from the globe on the left, which of course here is a perfectly round spherical surface that in fact is not the case, and then take that particular location and represent it on the right in some way that is meaningful and not misrepresenting what it is that we're trying to convey, the information that we're trying to convey. Well, there was a book a number of years ago written called How to Lie with Maps, and it's kind of like data. What exactly do you want it to say, and you can kind of make it say that, but you can be very misleading and probably most importantly, inadvertently misleading unless we understand all of these foundations. It's very critical to have knowledge of this stuff. So we hope in this little short segment that you have gained at least a basic understanding of these concepts, the ones included under the Conceptual Foundations, and with that knowledge, you will have kind of a base knowledge in which you can go out on your own and explore these models, explore these theories at a greater depth, so that you'll be ready not only for the exam, which is of course just the kickoff perhaps to your career, but more importantly that you have this knowledge so as you move forward in your career, you will be able to explain these things to people and not be somebody who is misleading yourself or someone else inadvertently as to what's being shown, where it came from, and how it's represented.
So Gary, we have a number of questions that I've seen pop up in the chat room. One that was most recent, and then I'll let Wendy jump in on some of the other ones that are there, was how much detail do people really need to understand with regard to things like the mathematics behind map projections? In other words, do you need to have a PhD level of knowledge to take this exam, or do you need something different? It's a great question. I thought you'd like to handle.
That is a good question, and I am probably not in a position to answer that very well. Wendy may have more information on exactly the level of knowledge. I would expect that people do not have to have a high level of understanding of calculus or geometry in order to pass the exam. But if you're going to get involved in developing these types or analyzing these types of models, then that becomes very important. I don't know if Wendy has more information with regard to the exam or not.
Yeah, I don't have any specific information. I don't think anybody really does on what is specifically covered in the exam. But you would think that, you know, it's more of the basic concepts. Someone else had a question, and we don't know exactly if we're going to know the answer to this. Does this correspond to the study guide online, or do we know if the study guide covers the right material? I'm assuming we are talking about the study guide that GISCI put out to help folks out, and I'm assuming that they would put out something that covers the right material. She also noticed that Gary didn't go over the spatial modeling according to Goodchild Demers. Gary, do you know what that is?
I do not, and that would be a true observation.
So Wendy, let me make a couple of observations about the questions. They're very good. The GISCI currently, at least when I looked a few days ago, has a number of different resources on their website that you could leverage to study and prepare for the exam. Some of those are developed directly by GISCI, some of them are not, they're just contributed. I think the study guide that might be the one that's being referenced is one that was contributed by a user that took a lot of time to put together a lot of resources. So our materials that we're going through today are designed to address specifically the things that you see listed under the KSAs, which is the limit of what the GISCI has specifically told people that they need to be familiar with. So other things that you may find in the study guide that I believe was developed by a third party that you can find on the GISC website are useful, but they're not definitively suggesting that those things are on the exam exactly as they are. A good example is the question that was asked about coordinate systems. I teach graduate level geography and GIS at my university, as well as being a practitioner. When I'm talking to a graduate class, I may be looking into or asking them to be familiar with the mathematics behind projections. I would venture to say that the vast majority of GIS users don't have a clue what the specific mathematics are behind the projections. But what they can and should know is what the basic properties of those projections are. So what is a datum? What is a coordinate system? What are the properties of a projection? You know, the old acronym SAD, shape, area, distance, and direction, that every first-year geography student learns. So those types of things are important, but you know, and we're not telling you this authoritatively. No one can. When you take a prep class, other than GISCI itself, but everything that I have been told in conversations with GISCI staff suggests that they're not looking for you to be an expert on the detailed formulas of a thing like a map projection. So hopefully that helps a little bit. Good questions. Wendy, are there other questions that we should try to tackle?
I don't believe so.
All right, very good. So Gary, I appreciate you going through the material. What I'm going to do now is pause the recording, and at that point, if you can stop the sharing of your desktop, and our next presenter, Zan, can activate hers. We'll start our next segment then in 5 minutes. Zan, I'll ask you to introduce yourself and maybe talk a little bit about your background before you jump into this. I meant to do the same with Gary. I've said at the beginning of the session this afternoon that we bring to the table today a group of true subject matter experts in their area, and you certainly are an example of that given your background and responsibilities. Also, I do want to comment that you know, the materials that we're presenting this afternoon are designed to provide you some guidance, not absolutes. As an exam, there are always possibilities that you're going to find things that we do not explicitly cover. But what is very solid for me to say is that if you have a pretty solid understanding of each of those main topics that are covered on the first few slides that each presenter puts up there. That is straight from the GISCI's website, and representatives from the staff of GISCI have been engaged in previous offerings of this. So we're comfortable that what we're sharing with you this afternoon is relevant and should help guide you in preparation for the exam. That is certainly our intent. I do encourage you to continue to ask questions, and we will do our humble best to make sure that we get you answers. We are also in contact with GISCI during this event, so if you have questions that we can ask of them, we certainly are happy to do that. So without further ado, Zan, I'm going to turn the floor over to you, and looking forward to this session.
Wonderful. Thank you so much. My name is Zan Fredericks. I'm a U.S. Geological Survey cartographer and the LIDAR coordinator for our Coastal and Marine Geology program. And I also serve as the Southeast Region LIDAR point of contact within the USGS. Externally, I'm active in the American Society for Photogrammetry and Remote Sensing, or the ASPRS. I serve as the GIS Division Assistant Director, as well as the Vice President for the Florida region. What you need to know when it comes to the second knowledge category for cartography and visualization, there are 6 key elements: a knowledge of contour mapping, a knowledge of basic physical geography, an understanding of how data collection methods influence map design and representation, also a knowledge of graphic representation techniques, including thematic mapping, multivariate displays, as well as web mapping. Having a knowledge of the principles of map design. This includes symbolization and color use, typography, not topography, also important though. And you need to have this understanding of how this impacts a variety of print and digital formats. And the 6th key element would be the understanding of how the selection of data classification and the symbolization techniques affect the message of the thematic map. So let's get started with the first key element, or contour mapping. Think of this as a delineation of any property in map form by constructing lines of equal values of that property from available data points. Contours are used for depicting a 3-dimensional statistical surface on that flat piece of paper or your computer screen. For topographic maps, this would be a delineation of elevation. On the graphic on the left, you see crustal thickness. The graphic on the right, you see sea surface temperatures. It's important to remember contour intervals when talking about contour mapping. What is appropriate, what is an appropriate contour interval? You have to know your data and know your message. If your contour interval is too wide, you'll lose features. But if it's too close, you'll lose your audience because it makes for a very messy map. Also, understanding what contour intervals can tell you about the data. If they're closely spaced, those contours are closely spaced, then that's indicating a high rate of change. Again, I'll use elevation as an example. That would be a high slope region. Conversely, if they're widely spaced though, that's a low rate of change. Again, back to elevation as an example, that would be a low slope region. What do the closed lines, the ellipses or the circles on a contour map indicate to you? Usually that's a hill or a peak. But if it's hatched inward, you need to remember that that indicates a decrease in value. Label placement, that's another key element to understanding good contour mapping. If you place a label on top of a line, sometimes it's really difficult to read that label if you don't eliminate the line running through the label. You need diligent placement, and remember to adjust those labels if it's necessary. Make sure you have a good understanding of ISO. ISO meaning equal distances between lines, but oftentimes you'll hear in contour mapping a variety of ISOs. ISO lines and ISO rhythms cover all types of contour lines, but then the subcategories are extensive. Isotherms, lines that connect points on a map that have the same temperature, similar again to that graphic on the right. And isocline, those are lines joining points with equal slope. I'm based out of St. Petersburg, Florida. I pay attention to isohumes. Those are equal humidity values. Isopleths are contour lines that depict a variable that cannot be measured at a point. So instead you have to calculate from the data collected over an area, something such as population density. It can be done using interpolation, but then it would be represented on a contour map using an isopleth. So contour mapping is the first of the 6 key elements that you'll need to have an understanding of for cartography and visualization. The second key element is basic physical geography. Physical geography attempts to determine why natural phenomena have a particular spatial pattern and what's that orientation. It examines and investigates natural phenomena spatially. It goes all the way back to Ptolemy with the understanding of latitude and longitude. But you need to remember physical geography's primary subdisciplines that study the Earth's atmosphere. So think meteorology, climatology. It also studies animal and plant life, so biogeography. Also the physical landscape, or geomorphology. Soils, or pedology. And also waters, or hydrology. If you are trying to show environmental degradation of the hydrosphere, or the atmosphere, or the lithosphere, or the biosphere, and show resource use issues, or perhaps a response to natural hazards. Again, I'm from Florida, so this past hurricane season, we're trying to visualize those kind of data, but we need an understanding of basic physical geography in order to make a map that's appropriate for the audiences. Also, it's great for environmental impact assessments and the effect of urbanization and land use change on natural environments. Another aspect of physical geography that would be good to revisit would be your plate boundaries. Have an understanding of divergent versus convergent versus transform, or it's also known as strike slip, and your continents, your landforms, the topography, and also a good understanding of the differences of scale. Is it temporal? Is it a spatial resolution, so time and space? Is it a relative scale, or is it a historic scale? Basic physical geography would be the second of the 6 key elements to help you with the cartography and visualization portion of the exam. The third is how data collection methods influence map design and representation. For this key element, you need to take into consideration the spatial scales at which information should be collected, also how it's compiled, analyzed, and displayed. The 2 graphics in front of you, I think, are a great representation. On the left, we see the different predicted paths for Hurricane Irma as she was coming up the Florida coast. Now imagine if that scale was similar to a graphic on the right. Floridians such as myself would have had no idea if I needed to evacuate because I was not sure, because the scale was much too large for me to be able to tell where her projected path was. Data sampling strategies and experimental designs affect and influence map design. Data representation, methods for the data analyses themselves. A field map. The field geographer's interest in distributions and spatial patterns is part of a larger concern with the synthesis of those data. So how and why particular phenomena come together in a specific place to create distinctive environments. So this concern leads geographers to observe and study a wide range of physical and social phenomena in the field. But again, how would you represent those field data knowing that your scale is much different than if you were trying to predictively model an epidemic at a global scale? Similarly, another perspective would be remotely sensed data. They're very useful in creating and updating maps of physical and biological and cultural features at the Earth's surface. And the ability of certain sensor systems to see through cloud cover and their unrestricted access to portions of the Earth provide information that may not be available from other sources. So again, that data collection method would influence your map design. Remember to refresh yourself on the distinction between primary and secondary data sources. Primary data is collected by the investigator themselves, whereas secondary data is collected by someone else for some other reason, but it's still usable to that investigator. Refresh yourself on the benefits and limitations of both. If it's primary data, I collected it if I'm the investigator, so I made sure to get the data I needed to provide me with the information I was hoping to get. If it's secondary, I didn't have the cost to collect it, but goodness, it may not meet all of my needs. Also, remember the 5 major types of data collection in geography. That's physical measurement, observation of behavior, archives, explicit reports, and computational modeling. And understand perhaps some of the ways geographers and others have made a distinction between quantitative and qualitative methods. Remember, quantitative data is measured numerical values, whereas qualitative data are non-numerical or with no quantitative meaning. They're more categorical. So how data collection methods influence map design and representation is the 3rd key element out of the 6 for cartography and visualization. This is a good graphic to show you the difference between quantitative or single variable representation and also qualitative. The 4th key element are graphic representation techniques. General maps emphasize location and relativity of geographic features and phenomena. We know that. We know that's how maps work. Thematic maps emphasize patterns or spatial distributions. They can illustrate the spatial variation of a single phenomenon or variable, or the spatial relationship between 2 particular phenomenon or variables. In thematic mapping, we've got chloropleth, if you remember to normalize, that's a key. And areas of graduated gray tones or colors can show spatial variations in the magnitude of those phenomena. Now remember, sites such as Color Brewer, they're out there and they can help you visualize the impact of those colors, especially for audience members with green or red color blindness or even monochromatism. They may not be able to see any color at all and just see things in grayscale. So another good representation is also, what if somebody photocopies your map and they don't use a color option? There are sites out there that can help you visualize your data and the impacts it will have before you finish your map. Remember proportional symbols and isorhythmic and isoplex as we talked with the contour mapping. You could also use dot maps. Multivariate displays are another great graphic representation technique. You can create a composite or use superposition with rasters and vectors. The key to a good multivariate map is to show the series as individual maps and then the final amalgam. Here we see a map for reading, writing, and earning money. Again, readings shown in the magenta on the left, writing in yellow, and earning money in blue. If your eyes are unable to distinguish out of the multivariate what color or what combination it's trying to show, you have those individual series in order to get a better understanding and feeling for your geographical area of interest within a multivariate map. Data uncertainty, such as spatial or temporal or even attributes, and how do you represent that? You need to classify representations of uncertainty into 5 basic types. You could have a traditional, you can have split map displays, you could have toggled map displays, you could have integrated symbolization on a single map and animation. And finally, web mapping. More and more in today's society, we're seeing web mapping, but don't be misinformed to think that all web maps are good just because they're out there. Give yourself a little credit as GIS users and make sure that your web map is appropriate for your audience and that it's usable on different platforms so it doesn't get cut off or the zoom level set arbitrarily. Graphic representation techniques are the 4th key element out of the 6 for cartography and visualization. Our 5th key element are the principles of map design. We see them here listed out, the large ones. These are things like layout. What's your position on the paper? What's the general organization of the map and its elements? Is there an inset? What's the visual hierarchy? What's going to stand out to your map reader? Symbols. Consistency for series. If you are doing a series of map, check what the standard is. Make sure that it's consistent across your series. Otherwise, you're going to lose your audience if they revisit a previously published map or a future map. Is there a standard for your industry or even your company? Make sure you use the same symbols, again, for that consistency. And symbols are shapes. If you hear the term symbology, that's the set of rules about how that shape should be used. Are you providing the accuracy and error? Is it represented? How is it best represented on your map? What about the scale? There is a difference between size versus scale and how that affects map design. Do you have a scale bar? Is the generalization of large scale versus small scale, which most appropriate for the data you're trying to represent? How about your symbolization variables? To me, that's the weight or the direction, even the proportion or the balance and the contrast of your variables and of your symbols and how it's best absorbed by your audience. Again, your typography, not to be confused with typography, but the text size, the font, the kerning, which is the spacing between the text, even the alignment and the orientation. It truly impacts map design and the readability. Even the color of the typography. The left graphic you see won't communicate well to people with red-green color deficiency because the saturation of the red and the green is too similar. So again, we go back to using a site such as Color Brewer or additional ones to have a feel for different members of your audience. And while it's not listed on this slide, to me, source is a large principle of map design. Do you trust your source? Should you trust your source? Is it listed? Years ago, there was an impressive statistic that visuals are processed, I think it was 60,000 times faster than text. This was a really popular statistic. It's since been debunked. The important lesson and reminder by me throwing that statistic out there, it sounds really impressive and I would love as a visualization person to adopt it and use it, but it's not, you can't take every statistic or data set or source as trusted and true. Don't perpetuate it by reusing or reciting statistics without doing a little homework. Remember that your GISP, if you are able to attain it, there's a code of ethics. Make sure you source your data and make sure you do your homework. There's so many important principles of map design. The ones I have listed should prompt you or remind you of the others. And it's the fifth key element for cartography and visualization. The sixth and final key element is how symbolization and data classification techniques affect thematic maps. We can make it easier for map readers to interpret maps if we match the visual characteristics of the map symbols to the characteristics of the data. There is no standard cartographic sign system that map readers have agreed upon at large that I'm aware of. Cartographers can match any symbol to any type of map feature. However, creating map symbols without carefully thinking about how they may be interpreted is likely to result in map readers drawing incorrect conclusions about what they see. Cartographers have come up with a series of guidelines about how to match different visual characteristics that we can use for creating symbols to the characteristic of the data set. Two characteristics that might influence how you choose which visual characteristics to use would be spatial dimensionality, as well as the level of measurement. So data can be collected at various levels of measurement. I'm thinking nominal, ordinal, interval, and ratio. So think of nominal as qualitative. Your hue, what about the shape or the arrangement and the orientation? Where I think of ordinal more as the quantitative or the value. How about the saturation or the size and the spacing? You've got different classifications that can help you. Equal range, quantiles, standard deviation, natural breaks. Make sure you review those to help you understand how your data classification techniques will affect a thematic map. Because you may be highlighting an outlier that you don't want to be highlighting, but you also may be covering it up and you don't want that to happen. So in order to prepare for the cartography and visualization portion of the GISP exam, remember to brush up on contour mapping, have an understanding of basic physical geography, make sure you understand those graphic representation techniques and the principles of map design, and have an understanding of how data collection methods influence map design and representation, and how symbolization and data classification affects thematic map messages. So I included a few GISP practice exam questions from the cartography and visualization section, and I'm just going to read through these pretty quickly. So the first example is in a map showing contours. The name of the darker contour line is, choose the best answer. For this one, it's A, index contours. Again, these practice exam questions are just to give you a feel of what you might see in the cartography and visualization section. The second practice exam question would be the inherent ability to suggest pattern in the phenomena they represent is a fundamental use of. Again, choose the best answer. In this case, it's A, maps. A small scale map would show, choose the best answer. Again, and I'm highlighting choose the best answer because you'll see that it's not always choose the best answer. But for this one, it's a larger geographic area than a large scale map. Because again, if we're talking about small scale versus large scale when it comes to a map, the best way for me to remember it is in a small scale map, buildings appear small or your item of interest appears small. In a large scale map, your item of interest will appear large. When mapping sensitive data, what are some techniques that can be used in order to avoid revealing details of the data? Select all that apply. So for this one, the answer would be A and D. Show the data as a heat map, as well as aggregate the data into quantities using graduated colors symbols or proportional symbols. And finally, how does using multiple attributes by category make a map more informative? We're back to choosing the best answer. And for this one, it's B. It provides the reader with multiple layers of information that are easily recognizable on a map. Those were just some examples of practice exam questions to make you more familiar with what you can expect on the cartography and visualization section of the GISP exam.
Thank you.
I'm available for any questions. You're welcome.
This has been great. I actually did not get a chance to hear you present in Jacksonville, and now I know why everyone was so pleased with it. I appreciate your time. I know that you're on the road and squeezing this in. Wendy, are there questions for Zan?
It looks like there's one. Zan, somebody wants to know if you can revisit the part where you talked about traditional split map, toggle map display, integrated symbolization, and web map, and classify.
Certainly, I'd be happy to. Right, and that goes back to me, that's going back to the graphic representation techniques and data uncertainty and how you can represent that. So again, remember, data uncertainty is a spatial, temporal, or looking at even your attributes. So I think of it as classifying those representations of uncertainty into those different types. So be sure to look up the traditional way of representing the uncertainty. Or if you could split it, again, what is that uncertainty? How is it best to visualize that uncertainty? You can toggle it. It's kind of that before or after. Now you're seeing lots of slider bars. And that's a good way of showing uncertainty, because again, I don't want to get into too many specifics, because what level of uncertainty are we talking about? It will depend on your sigma values and things like that. Or you could go into an integrated symbolization on a single map, but it can be tricky because sometimes your uncertainty is rarely the same across your entire map. So you need to find a way to correctly represent it for what scale your data should be represented at, or what scale you've chosen to represent your data. So again, think of it, those basic types that I was talking about, you don't need to research them individually as, oh, what is a split map display? But think of it as a way of representing uncertainty as part of the larger graphic representation technique.
Sounds good. And another question, what are the different measurement methods? Physical measurements, explicit reports, and then what were the others?
Okay, so the different measurement methods that I was talking about, we've seen them all across the board. And listen, I mean, maybe it's not, again, as Kevin was saying earlier, it's one of those that I hesitate to simply say these are the only measurement methods, because I would like to make sure that people understand that it can be collected and compiled and analyzed and displayed in different ways. So again, I don't want to make people just take notes on what I've said and forget the other aspects, because in my mind, we need to cast a wide net when we're studying for the GISP exam. And that includes asking peers and colleagues and even supervisors if they have a cartography anecdote or if there's a map fail that stands out to them. I know I'm digressing and I apologize. I see this as an opportunity to refresh and update your cartography and visualization knowledge. And to me, it's the case with many exam preparations, is that I hope people come away with more knowledge than they were expecting to get, and it reminds them why they started down this path. So I'm hoping that we were able to put the kernel of truth out there and people dig up more what they see as important, because again, I'm coming from my perspective as my personal experiences with this. So I would recommend people perhaps using different study guides. And as Kevin was saying earlier, I found those study guides that are available via GISCI to be still applicable to the exam as it's going on now. So perhaps revisit those as well.
Perfect. Thank you so much, Dan.
Thank you.
Are there any other questions? These are good ones.
It doesn't look like it.
Well, Zan, I do appreciate your time. I hope everyone benefited as I did. I learned something new every time I have a chance to talk to you or hear you speak. I think by now everyone should understand this, but this workshop that you're attending today, this alone cannot possibly prepare you sufficiently for the exam. It does require study. So that was brought up on the call yesterday, and I'll just remind everyone that that is the case today. I've been personally doing GIS for well north of 2 decades now, and last time I took a credentialing exam, I spent 40 hours studying for it and was glad that I did. So I think the same would be true here. I suspect even someone like Zan and our other presenters, were they to take this exam, would spend some time studying for it. We all studied preparing to put this webinar together. So Zan, I suspect you probably agree with that.
I couldn't agree more. I would feel that way too. And I do realize, Wendy, I'm sorry, it just came back to me. I'm being pulled in multiple directions, but I think what the person was asking, and I do apologize that it took me this long to get to that, was if they were asking about the physical measurement versus observation of behavior archives. There was also explicit reports and computational modeling. So if that is what the person was asking, please bear with me. I do apologize for digressing completely in a different direction.
But interesting nonetheless. All right. Well, I do appreciate your time, Zan, and we'll let you get back to your other commitments today. I will pause the recording. And Al, if you would like to introduce yourself, a little bit about your background, and then jump right into your topic, we'll carry on from there. Again, for any of you that have joined us in the last couple of moments, feel free, and I encourage you to open your chat window. You are muted, and we do that to make sure the quality of our recording is good. But I encourage you to use that chat window liberally. There's interaction going on as questions come up. And when Al gets through his content, we'll also, our colleague Wendy will voice any questions that haven't been answered to that point so that Al has an opportunity to respond. So Al, the floor is yours.
Oh, great. Thank you, Kevin. My name is Al Carlin, and I'm a spatial scientist with the Southwest Florida Water Management District. I've kind of been in the geospatial business now for the better part of 30 some odd years. And unlike many, I am not a geographer. I'm a statistician. So most of what I do, unlike what Zan does, is more from the numerical sides of things. But however, like Zan, I have been active with both GISCI and with the American Society of Photogrammetry and Remote Sensing. Both at the national level, like Zan. I've served on several committees. I serve on our LIDAR committee, which is where my area of expertise lies. And I've also served here in the state of Florida as our president. I'm our immediate past president, and I've been on the board for a long time. So with that, I want to talk just a little bit about the geospatial data section on the GISCI qualifying exam. And this particular knowledge area includes 6 sub-areas. It includes metadata and knowing metadata standards, understanding the difference between quality control and quality assurance. And to that end, one of the things that I do for the Southwest Florida Water Management District is I manage our quality control team, our QC team, for both photogrammetry and LIDAR and other remote sensing projects. So we'll talk a little bit about that. The third area of knowledge is regards data archiving and retrieval, data storage, the things that are required sometimes by law, state law and statute for data storage. The fourth area revolves around knowing some real basic geoprocessing tools, joins, merge, unions, clips, and intersections, which of course all have their basis in mathematics. Fifth area is a knowledge of basic geomatics. And being a bit of a geodesist, we'll talk about things like datums and projection systems. And again, as was mentioned before, I believe this doesn't really require the mathematical understanding, but just a basic knowledge of how to use them, what they are, and when it's appropriate to convert data and how to convert data between datums and between projection systems. And then finally, some basic field data collection techniques and methodologies. All told, although this is section 6 and I'm kind of out of sequence because of my personal schedule today, area 6 accounts for about 13% of the questions on the exam. So, you know, you're looking here at about a sixth of the exam. So the first area of knowledge revolves around metadata and its standards. And of course, metadata are the data that describe the data that you've got. And for a long while, there were a lot of different standards floating around out there. And toward the early 2000s, late 1990s, the Federal Geodetic Data Commission, the FGDC, published a set of standards after industry-wide consultation. Those standards are available obviously at the fgdc.gov site, and I encourage people to go and at least flip through the standards. Now, my goal in my presentation today is not to teach a whole lot, but just to provide links and direction to where you can find those things that are outside of the materials that are available at the GISCI site. So the authoritative place to go is the FGDC for metadata standards here in the United States. There are several metadata standards that the FGDC uses. They have their own FGDC authored standards and the ISO standards, and I give you links here for both of them. And in either case, there are hierarchical standards and there are fields that are to be completed. Now, one of the things that I want to make, or that I have to make, unfortunately, real clear, is that I'm not endorsing or advocating any one particular software product or any particular firm or anything, but I think most of us who are Esri users, and my district is an Esri shop, we make use of the Esri metadata tools. And to be quite frank, I think everybody realizes, or everybody should realize, that some of the Esri metadata tools work well and are absolutely compatible with FGDC standards. Some of them are abbreviated, and you just got to be real careful when using the standard Esri metadata tools when constructing metadata. They are available, and through the Esri metadata tools, there are several different implementations. So, you know, once again, my advice is look at the Esri metadata descriptions at the ArcGIS site, and at least be peripherally familiar with them. The last thing that I want to comment about metadata is that everybody should be aware, and if you're not, you know, I don't have a slide for it, but it's a real good thing to use the USGS metadata parser. And if you just go ahead and Google at your leisure, USGS, that's the United States Geological Survey, metadata parser, it'll direct you to their site. And at the site, what one does is just use the site directed to either an XML file or a metadata source file, and it will parse through the metadata and provide back a report for you describing the fields that are either incomplete, that absolutely have to be complete to meet the standard as error fields, and it will also report warning fields, those fields that are not necessary to complete but are advantageous. So once again, basic knowledge of metadata. Go out to the FGDC site and be aware of the USGS metadata parser. The second area refers to knowing the difference between QA and QC. And by basic definition, QC, quality control, refers to how the product is. And one determines the quality control by testing a sample, or in some cases the entire product, against the specification. Whereas quality assurance is more a process-oriented thing. It's how you go about collecting data, how you go about making sure that the product has been produced by a standard operating procedure that's acceptable for that particular product. So in the case of my district, we are not particularly involved in quality assurance. We purchase data from a consultant, and it's their quality assurance process that we rely on. However, once we receive a data set, then we sample that data set through our quality control processes to ascertain whether or not it meets the standard that was specified for that particular product. Frequently, one looks for standards, again, for both spatial standards and attribute standards for different types of products. And again, I'm providing some information as to where to go to find those sorts of information. The ISO Geographic Information Standards page there by the committee.iso.org provides a list and some guidelines for specifying geospatial products in terms of things like attributes, the types of fields for each different type of attribute, and on, and the ASPRS, the American Society for Photogrammetry and Remote Sensing, is heavily involved in spatial accuracy standards. So if you go out to the www.asprs.org page, look for the photogrammetric division. It's there that we have accuracy standards and how they're to be measured. Good standards for measuring horizontal accuracies, vertical accuracies, whether we're dealing with GIS collected data, survey collected data, remote sensed types of data, and on and on and on. So, these are all good sites, good places to go to look for those sorts of things. The third area of knowledge deals with data archiving and retrieval. And as everybody, I'm sure, is well aware, one of the main functions of a GIS data system is to store data in such a way that it can be easily retrieved and used again. There are, again, I think it's important that we know that there are several different types of file formats out there. Some of the file formats are more portable than others. Each of the file formats has advantages over each other. In our case, I think everybody should be aware that zip files can only contain so many records. RAR files can contain more. TAR files are an older format that's pretty much universally understood for data compression, and that each of these data compression methods has, again, advantages and disadvantages. If you're, again, if one's looking for standards for data archiving, and particularly in our case for digital data archiving, the state of Florida has a standard to which all of the public agencies are required to meet, and those standards have been the standards have been codified, and they're available on a website. So here's a good general area to look to understand and learn how data, in this case digital spatial data, are to be archived for perpetuity and for ease of retrieval. The fourth area of knowledge in this knowledge area are just some of the very basic geoprocessing tools, joins, merge, unions, clips, and intersections. And once again, these are mathematical set operations designed or brought into the geospatial world, again with very special and unique capabilities. In the case of a joins, of course, we're going to use to join spatial data to tabular data through a selected field. Mechanically, it's done differently in every GIS system, but there are some common threads that we all see, and that they generally involve some kind of an indexed field that has to occur both in the spatial data and in the tabular data. So we look at that as a tabular join, or we of course can do a spatial join where we join tabular data to spatial data simply on the basis of geography. For the other geoprocessing functions like union, intersect, clip, and merge, these are acting on spatial data sets. And again, it's basically a mathematical understanding of what the differences between unions, intersects, clips, and merges are going to do. I think on the very superficial basis, to understand that when we do a union, we're going to put all of the data from two or more spatial data sets together. When we're doing an intersection, we're looking at only the place where two or more data sets are intersecting each other or overlapping. Clips are used to reduce the size of a data set, whether it's a raster data set or a vector data set. And of course, merges we use to merge data that from spatial data sets that have similar content. So again, it's just a general overview of what these particular geoprocessing functions are used for. The fifth area of knowledge is one that's near and dear to me, and it's basic geomatics. The use of projections, coordinate systems, and datums, and understanding what they are. Again, my goal here wasn't to instruct so much as it is to provide links to other places where one can go and get the information. So here, I show a couple of basic projections, the Mercator or cylindrical projection, an Albers conic projection, and an Azimuthal Lambert projection. I think here the idea is to recognize that different projections, some are used to preserve areas, some are used to preserve dimensions, and each projection has its own value and purpose. So generally to be familiar with what the general projections are and how and when to apply these sorts of projections to your data. You know, one of the things that ArcGIS does, of course, is it automatically projects between data sources as long as the projection system is known, and sometimes that can get to be a little bit dangerous. So I think that's the role of this area of knowledge. When we're talking about coordinate systems, sort of the same thing. We need to understand how we go from spherical coordinates, the degrees and minutes, seconds, and latitude and longitude, to planar coordinates through projection systems, and things like that. And again, you know, here are a couple of links. Again, I just want to make it very clear, I'm not endorsing any particular software or web links, but you know, here's just a couple, an academic and of course one going back to ESRI. One of the other things that I'd like to make everybody aware of, if you're not already, is that here in the United States, the coordinate systems, datums, projections are all basically maintained by the National Geodetic Survey, which is a branch of NOAA. Here's one of a link to one of their data transforming packages. This happens to be in beta right now, but it transforms degrees, minutes, and seconds into other projection systems, or I'm sorry, into other coordinate systems for you based on datums that are input and projection systems that one wishes to use. This is probably the Cadillac, if you will, of projection systems, where all of the mathematics is as accurate as the mathematics that we can ascribe to these sorts of things. The last thing that I want to talk about in terms of basic geomatics is understanding what datums are. And of course, the definition of a datum is just simply a reference plane or a surface. And here in the United States, we have different reference planes, surfaces, that we use for horizontal measurement and for vertical measurement. For the horizontal measurement, it's either NAD 27, the national, the North American datum of 1927, rather, which has been pretty well 100% replaced by the North American datum of 1983 with various adjustments. And here again is something that, you know, one kind of needs to be aware of. The Esri software has lots and lots and lots of datums, some of which are not recognized by the NGS NOAA. And one of my favorites here in Florida is HARN. And everybody wants to use, or wants to, for some reason, use NAD 83 HARN. And HARN is just a minor alteration of NAD 83. The current datum that's recognized by NGS is NAD 83 with a 2011 adjustment. Similarly, we have vertical datums, and the current vertical datum is the North American vertical datum of 1988, which references, and this is where things get a little hairy, and again, I don't want to teach, but one of the things that I think in terms of vertical datums that we as a group need to understand are ellipsoid heights and geoidal heights. NAVD 88 references to ellipsoidal heights, which is a theoretical average height for elevation for the Earth. Geoidal heights are the normals to that, which represent the actual Earth surface. So one has to convert ellipsoidal heights to geoidal heights using a conversion to get to elevations that you would measure on the Earth relative to sea level. And right now, we do that through use of geoidal conversions, and the geoid that we're using right now is the geoid of 1912 version B. All of this data, all of this information can be found with more clarification than I can possibly provide at the NOAA site, and those are the sites that I reference here. The unusual picture that I have on this particular slide, if you're unfamiliar with it, that's a gravitational image of what gravity around the Earth looks like. Places that are red are areas of very high gravity, and places that are blue are areas that are of lower gravity, lower gravitational force. And for those of you who do not know, the NGS and NOAA have been flying gravitometers throughout the continental United States and Puerto Rico, measuring gravity, and the vertical measurement, our NAVD 88 with geoid 12B, will soon, 2020, be replaced by a new vertical datum that's going to be called GRAV-D, G-R-A-V-D of 2020. So if you're interested, there's plenty of information out there on GRAV-D 2020 out on the NGS NOAA website. So things are changing. Things will always change, and we will be moving within the next couple of years to a new vertical measurement. And Lord only knows what havoc that's going to wreak on staff gauges throughout my district. So that's just a couple of other things, couple of other links here to tools that we can use to convert between the existing vertical and horizontal datums. So those are for you to investigate by yourselves. The final area of knowledge for this knowledge subunit is basic field data collection. And in this case, again, I'm not endorsing any particular equipment or any particular sites, but in terms of field data collection, going out in the field, obtaining new geospatial data, it's really a two-part issue. One part is, of course, finding and locating objects on the Earth's surface, and the other part of field data collection is defining the attributes that one needs to associate to those spatial positions, spatial locations on the Earth. There's all sorts of there are all sorts of guidelines and websites to help us understand or to help us define workflows and things like that, using equipment, using paper and pencil in some cases. And once again, I advise people to go out and look to your heart's content. Esri, of course, has produced a couple of new software packages, Collector being one of them. Trimble has their own software packages, and several of the instrument providers have their own software packages that go along with their instruments that will help guide you through the process of collecting field data. So my advice is, choose the one that you like and go out to their website and see how they do it. So with that, just to review the general knowledge areas for this particular area are metadata and its standards, QA/QC, archiving and data retrieval, basic geoprocessing, some basic geomatics, and field data collection. Along with that, understanding the significance of data documentation, knowing original sources, much of the things that Zan mentioned in the session previously. And then, of course, how to apply best practices to actually going out in the field and collecting field data. So with that, and as Zan did, I'll just go over a couple of the questions from the practice exam very quickly. And these are the questions that are on the website, and one can go and look at these and think about them. The FGDC has endorsed choose the best response, and as Zan indicated, I'll do the same thing because many of the questions will have more than one answer. You go down the answers, and in this case, D is probably the best answer. The FGDC endorses all of the standard ISO 19115, ISO metadata standards, as well as the FGDC metadata standards. With respect to collecting field data, and again, this question addresses two areas. One, the field data collection, and both a question about QA/QC, the issue. The value of pull-down menus, field choices in mobile data collection allows for certain data to be added without typing. This valuable input technique allows control in input syntax and is a proactive part of, well, in this case, the best choice there is quality assurance, because this is a process. This ensures that we don't have spelling issues and typos and mispunctuation and capital letters and lowercase letters mixed up in our fields in a geospatial database. So this is something that's done during the data collection process. So it's a portion of the quality assurance. Now, to go back and check, which would be a QC process, one would write a script and go through each field in a geodatabase to ascertain whether or not there are errors, omissions, or things like that. So that would be a QC process, whereas the process of collecting the data and using best practices to collect the data would be a quality assurance. What are the main reasons for implementing a data archiving system? When you look at the possible answers here, the cost of primary storage, ease of access to historic data, fast access to the most important data, and various data export and imports, I would select all of these. It just goes without saying that that's what GIS data systems are designed for ease of access to historic data. The cost of collecting data is so astronomical in terms of human time, in terms of machine time, in terms of data processing, that we really can't afford to lose it. And similarly, we want to be able to access important data quickly, and we want to be able to have data export formats so that we can use the data well into the future. Which of the following is used to extract features and their attributes? And I emphasize the and their attributes because I think those are the operative words in this particular question. From one layer, using a polygon from another as the boundary of the output. Choose the best option. And we want to extract the features and their attributes from one layer using a polygon from another layer. So I would do this with one of two ways, and you could do it with a clip, and that would extract the data from either a raster or a vector data set using the boundary of another polygon. So in this case, I would choose a clip. Which of the following is used to build new features by splitting overlapping features and combining attributes where the feature overlaps? Again, that would be a union of two data sets where we preserve both the geometry and the attributes of both feature data sets. Next, what are some important considerations when converting hand-drawn features from hard copy map to digital data? This goes to the question of to know what the quality of different data sets are. Colors really don't tell us much. The method, the field data used to orient themselves tells us something. But that's a reasonably good answer, probably a good choice. Determining the background data shown on the paper maps, which one is the most accurate to use for georeferencing it. Again, that's a good choice. And the ability to understand the notations made and to interpret the attributes for each feature are all probably good considerations. So I would more than likely choose B, C, and D for this question. And the very last one, when collecting GPS data, what are the most important factors in determining the accuracy of the resulting data? Well, using templates and prescribed schemas for feature creation to ensure data quality, that's certainly an important factor. The number of and distance between features collected each day. Again, that may be an important factor determined by the position of satellites, PDOPs, and things like that. So that may play a role. The capabilities of the GPS receiver and alignment of the GPS satellites at the moment the data are collected, that would probably be the single most important characteristic. The battery power of the data collection device, probably not quite as important. Most GPS receivers are designed to maximize the power and to basically stop when there's insufficient power. So of these, I would argue that A, B, and C are probably all good answers. If I was asking what the single most important factor is, I would choose C as the single most important factor. So just a couple of things to think about. And of course, I'm always happy to answer questions if anybody wants. You can get me at my email address there on the bottom. And according to my timer, I've used 35 of my 40 minutes, so we've got time for questions.
We do indeed. Thanks, Al. Wendy,
sure.
Questions?
I believe the group has answered their own questions. There was a question early on about if you could repeat your definition of datum, Dr. Carlin, but I think that's it.
Okay. The geospatial definition of a datum is simply a reference surface or plane. And it's the surface to which we reference coordinates, whether they're XY coordinates, horizontal coordinates, or vertical coordinates. So in the case of GPS collected coordinates, those coordinates are referenced to the ellipsoid, a reference, in this case it's a reference sphere.
Excellent. Well, we have no other questions in the chat room right now. Kevin, I'm proposing that there be an official break while we get the next section underway.
I think that's a tremendous idea, Wendy. I was going to suggest exactly the same thing. Everyone needs a stretch break, including myself. So we will reconvene at, let's make it 5 till. It'll give you a 7-minute one function break, and everyone can fill in the word function as they see fit. So we will reconvene exactly at 2:55 Eastern. We'll be right back. Thanks, Al. Cheers.
Good afternoon, everyone. My name is Lisa Fulton. I am a senior GIS analyst with the Coastal Regional Commission in Georgia. We are based out of Darien, Georgia, which is an extremely small town. Hesitate to call it a city, but the county itself is only about 14,000 people. But we are right smack dab in the middle of the coast, probably about 60 miles south of Savannah, so not too far. But anyway, I'll be talking to you guys about the GIS analytical methods section in preparing for your GISP exam. The other thing I wanted to mention was I'm also active with the Southeast Georgia ERISA subchapter. We are so far removed from Atlanta with the Georgia, where they usually meet, that we have been steering activity along the coast and a little bit inland. So anyway, we will move forward. There we go, a little quick. All right, so what do you need to know? From what I can tell and what I've seen today, this is the most in the sections. There's a total of 8. And since we're going to cover all of these in this slideshow, I'm going to not read them all right now. So much of my content does have resource links, so there's a lot of details that are not actually on the slides, and I highly encourage you, once you get the presentation downloaded, to go through those links, because there'll be a lot of information that will help your understanding and your logical thinking when you're trying to work your way through these questions. All right, so first one, knowledge of overlay analysis. Each of these tools, they're integral in finding answers and solutions to potentially complicated questions. Essentially, you're going to take 2 unrelated themes and figure out how they relate to one another. As we've seen in previous presentations, different types of data are treated differently, so you got to keep that in mind. We're going to talk about vector first. General overlay analysis. I've got notes and I lost my place, so give me a second. General overlay analysis, this simply brings multiple data layers, typically unrelated, differing themes, together to identify possible relationships that may exist. Further along the process, new data can be developed. And it may not be something you're expecting to see, so keep that in mind. Vector overlay tools, these are defined in 2 ways, by the layer types and by the tool function. Take a look at that more info. You can see the image on the right for identity, intersect, symmetrical difference, union, and update. I've recently seen a use for symmetrical difference and doing census data work. Let me see. And sometimes you can even use it for floodplain change comparison. Okay, moving forward. Getting on to raster. Understanding raster layer types is important when you get to these particular tools. Zonal statistics, combine, single output, map algebra, weighted overlay, and weighted sum. So getting into zonal a little bit, it develops an area of single value after processing from multiple data sets. See the link for good examples and representations of this. Combine, often layers are weighted and they're brought together. And this is considered an additive method. You would want to use a weighted method prior to combining your layers so that you can have the opportunity to apply a prioritization measure for your data. And you'll be able to adjust your values as needed. Fuzzy membership overlay, this is something I am not personally super familiar with, but I did my best to find some good resources for you. And there's different types. I can't imagine that you would need specifics, but definitely get an understanding and how you could potentially use them. And I do have questions at the end of the presentation. I think I only have 2 because there's so many sections for here. Planar geometry. This converts reality into spatial data using the following. So planes, these are flat, 2-dimensional. Points, coordinate pairs, lines is an ordered list of points, and polygons is just a connected ordered list of points. And we've seen in a few previous sections some of these concepts already. So when you're studying, I'm sure you're going to see some overlap. And as a teacher myself, make sure you give yourself plenty of time so you don't get frustrated by being confused. Be able to determine the best representation of a geographic feature, and going a little bit farther, of a geographic feature at a given scale. For example, points best indicate single locations, and lines will often represent a river. But if you're zoomed in, or you're on a larger scale, a smaller land area, you'll probably want to change that to polygons at some point. So to clarify and reiterate a little bit, this isn't on the slide. Small scale typically shows a large geographic area, and usually one or only a couple themes. Large scale typically shows a small area, and you can usually put multiple different themes while it's still being readable. So that's getting a little bit ahead of what I've gotten here, but I'll reiterate if I need to. All right. You need to have a good understanding of math algebra and where it's used. Not only where it's used, but how. I don't typically use Wikipedia, but it's a good starting point for finding other sources. So there's a link there. There's several types of algebra operations that can be used: arithmetic, statistical, relational, trigonometric, and exponential and logarithmic functions. In short, just make sure you have a good understanding of how algebra is employed in GIS, and it's employed in many different places. And when you're doing expressions or query, there's so many different places you can use it. You can use it when you're trying to represent data, or when you're actually doing analysis to get a specific answer, or to answer your question, basically. All right, so a knowledge of statistics. I think Kevin, Dr. Carlin would be, if anybody has statistic questions, he would far and away exceed my knowledge base. So keep that in mind. Descriptive. So in mentioning the use of statistics in the previous slides, it is important to have general knowledge of statistics separate from GIS. I'm sure the list here is not exhaustive, so treat the concepts as a starting point. All right, so understanding how GIS certain functions are done, and then how similar ones are done with statistics. So traditional GIS, you start with points, lines, polygons, and then with the spatial analysis, you use all those layers together to create a generated spatial relationship. So traditional statistics, when you're using standard deviation, a lot of those times will help you with visualization. Again, I have links here that'll give you a good basis for the specifics. Moving on. Basic programming. This one I understand a little bit better. Scripting. This is building code from scratch, line by line. In my experience, I've noticed that there's certain lines of code that you start with, and then you just build it from there. You don't need to know how to do it from scratch, but you do need to be able to identify what the block of code is trying to accomplish. So object-oriented programming, it uses collections of attributes in code in the form of procedures known as methods. Extensibility, this is a design that takes future growth into consideration. So with extensibility, when you're building it, you want to make sure that you can build upon it for future additions of data or functionalities that you see that your organization may need to incorporate. Keep an open mind. All right. Raster and vector principles. This one has been covered pretty well already. Be familiar with the definitions of raster and vector data. This graphic here does a good job of giving you a breakdown of how, say, for the first row, you've got hotels. It would be represented by specific cells in a raster. And then in the vector view, there'll be points. So as you can see on there, a raster can very easily generalize what you may not want generalized. So when you're making a choice of how best to represent your data and how you want it represented in an analysis process, how do you want the numbers to pull through in your method, it's extremely important. You wouldn't necessarily want the space that your roads occupy to be calculated in a generalized manner if you're modeling for that specific area. I'm looking at the time and I feel like I'm running quickly, but I think I'm doing good.
Yeah, you're doing fine, Lisa.
Okay. All right. So I mentioned scales earlier, as far as small and large scale, which I did my best to explain the basics of that, the difference between the two. So when you're representing it on a map, you've got a verbal scale, 1 inch to 50 miles. But you also have your graphic and your visual scales. A lot of times, organizations, or even when you're making them for personal interest, you'll have your what you want to show, but know that they're going to change. Okay, what are these? And sometimes the organization will show more than one. So representative scale, you have the large, medium, and small. An absolute scale, it's represented without units specified, which I find useful. I've got an example written out here. It's 1 to 24,000. Basically, any unit, 1 unit on a map equals 24,000 units on the ground or in reality. Okay. The scales are extremely important for GIS, and you need to understand how they're related and how they convert to one another. So this is another way that algebra plays a role. Again, I've given linked sources on here. For this slide, I want you to know the difference between abstract data and physical data. Abstract data, this is what we draw, but isn't actually there, like political boundaries. Physical data is your physical geography, actual features and structures, land masses and water. All right, more on units. Okay, units of measurement is our next section. So we already talked a little bit about conversions. You have angular and metric, and then you have basic common measurements. I don't know about you, but I've got a few of these memorized because I've done it so many times. And working with addressing, that 1 mile equals 50 to 80 feet kind of sticks in your mind after a while. Be aware of the units of measurements that you are using with your projects. They need to be consistent. And it's always better to catch numbers that don't seem quite right in development. This type of skill and eye does require some time to learn or a cheat sheet. Yeah. So common angular measurements, you've got the whole 360 and basic formulas on how to calculate from a radius or a diameter. All right, just a few example questions. And overlay analysis is based on this one would be D, Boolean logic. And some of the questions may be just that straightforward. I noticed that some of Dr. Carlin's questions were choose all that apply. And these are choose the best response. And choose the best response may be just one answer, but they may not be. As far as I can tell in this section, these two questions, which are included in that practice exam on the GIS CI website, these are one answer. Representing features logically in GIS format requires knowledge of GIS primitives. The scale at which a feature is intended to be shown can help define the proper primitive used to create and display that feature. The best option to represent a feature class for rivers in a statewide map would be this would be C. So again, I've included all of the sources that I found, my images, and the more detailed information that I wish I could have put on the slides to share with you guys. But once again, this is an overview. Definitely give yourself time to get through all of this before committing to taking the exam. Along with the resources provided with the study guides, I've included a few that I found helpful but did not have in previous slides. So I think I do have a couple minutes, and I may be under. Again, there's my contact information if you have questions on anything in particular.
Lisa, you're just right on time. Wendy, do we have questions in our chat room that Lisa can help address, or our other presenters?
No, we don't. There has been some discussion about programming and what's included with the KSAs. Zan has directed some folks to the proper pages in the study guide to cover that item.
Thank you, Zan.
Lisa, actually, I want to dovetail off of something that you mentioned a bit in passing, that you actually teach in a college environment, some GIS courses. One of the things that's really good, especially for young professionals, is that they should be coming out of that academic experience with a lot of the foundational knowledge that would be necessary for taking the GISP exam. And I would encourage those of you who are dialed in today to consider that, even though you may not qualify for completing the entire GISP application. You can get that exam taken care of, and to do that while it's fresh in mind is really a smart thing to do, because those skill sets, that terminology tends to fall away over time. Most of us that are practitioners focus our attention on a few parts of the GIS world, and the rest of it just kind of slips into the background. I'm one of the fortunate ones because I teach this kind of thing, but many people don't deal with that. So a lot of these concepts that we're talking about in the different knowledge categories can easily get grayed out. One of the things that we're attempting to do with this presentation today is to provide that reminder, if you would, about the things that maybe you've forgotten, that you need to refresh some skill sets on, and to provide some of those links. I really do want to acknowledge that there's been some tremendous sharing of resources and information as part of this webinar this afternoon, not only by the presenters, but by the participants. So please continue to drop links for ideas and so forth into the chat window. We've got roughly 60 people that are benefiting from that. So if nothing else, one of the reasons that I got engaged with ERISA to begin with is that I learned from others around me, and you're doing exactly that. So we have 6 presenters and we have 60 instructors. That's the way I look at it. So let's benefit from each other. If you feel like you just are losing track of the world occasionally, that's a reason by itself to get involved with ERISA, because we do nothing but talk about GIS every time we meet. So take advantage of that opportunity. There is a question that just came up about whether there's an opportunity to compile some of these links and tips from the chat. We're going to capture the chat and see if we can do something along those lines, and maybe post that in conjunction with the links for the recordings. Wendy, do you want to, I know that question has come up pretty constantly about every few minutes, whether people will be able to access these recordings. Do you just want to just talk through that, or talk to that right now, just since everybody's on?
Yes, I believe I mentioned that we will gather all of the PowerPoint presentations, turn them into PDFs, and post those along with the recordings. And you guys will all, as registrants of this event, you'll all get those links.
Yeah. Any idea what timing? I heard that question too.
I'll try to do it this week. I have to get to the ERISA GIS Leadership Academy starts on Monday morning, so I'll have to get it done this week.
Yeah, sounds great. All right. Well, in that case, we're going to go ahead and I will briefly pause the recording. And if you would like to, please introduce yourself. I know you have a phenomenal background and a lot to offer to the group today. So the floor is yours, my friend.
I'm someone else from South Florida enjoying the wonderful weather today. I am a past president of ERISA, been active in the workshop development committee, have participated in the development of a curriculum for a 2-year curricula in the Geotech Center for small colleges. I've worked with associate certificate programs. Currently, I'm working as a cloud architect for some federal clients trying to improve their responsiveness by moving certain applications into cloud. I have a long GIS background, dating back to the very early 80s. So that's enough about me. So I can't see the screen. Can you?
We're not in presentation mode. If you're, I don't know if you can go into slide mode or not, but if you can't, that's okay.
Yeah, and I'll get there. I'm on the Mac, and Mac's not my. Here we go.
Still not in. There you go. Perfect. Tab away.
Okay. And just make sure we're in a good spot. And we're at the right time. Okay. So some of the things that we're going to touch on here will seem like they touch on topics we've already covered. There is an awful lot of interplay between these topics, and they're not all entirely distinct. So I'm not going to avoid them where they touch, but certainly where two topics touch is an area to pay a particular attention. We're going to talk about knowledge of making spatial selection queries and how you would do that, methodologies, maybe even a little bit about different programs and how they do them slightly differently. You should have a knowledge of the different types of storing information and the idiosyncrasies and limitations, features of them, and formats of geospatial data, spatial data, rendered data, and tabular data. You should have knowledge of different field types, including to a degree the jargon used with describing them. Sometimes there's more than one way to describe a field type. We'll talk a good bit about data relationships and consequences of that, especially with regard to statistics and aggregation. We'll talk about data collection, transfer, and conversion, and where you lose information, where you save information, and some other issues. And then knowledge of data quality, and that'll touch a little bit on quality control, quality measurement, and then fitness for use. I am both a Esri user and a open source GIS user, and so I'll have some screenshots from both. Some things may look familiar. So there are both attribute selections, spatial selections, and other. So there is a topic of the DE9IM, the Deterministic Entity 9 Intersection Matrix, which talks about the way that geospatial objects can intersect. And over on the right side, we have a few of these types of entities talking about that. It would definitely go through and be sure you knew all of the types that geospatial entities can relate and the words to describe the relationships within them. It is possible that a single graphic might manifest more than one type of geospatial properties. There are attribute selections as well, and when making selections, the way you would do it in QGIS, in ArcGIS, doing it in Python, doing it in SQL, they all have similarities. They all have methods that will enable you to get to the same outcome, but they have slightly different idiosyncrasies in which you format the query. That's a place where I would pay particular attention is the way that you would use, say, ArcPy or Python to make spatial selections versus using selection tools to understand the differences between them. That's a place where knowing programming languages can help you understand what's happening with the queries. Data store types, we should all be familiar with things like shape files, file geodatabases, personal geodatabases. So just to talk about the spatial, you should know which ones are the least compact, which ones are the most compact. You should know what types of data can be put into each of them, what types of data can't. You should know where data gets lost and how hard it is to retrieve data from, or expensive it is to retrieve data from different formats. We don't have on the spatial side enterprise SQL databases, but those should also be in there. Things like GeoPackage, which are client or desktop SQL databases. Should know things like raster data sets and how they might be rendered through TIFF, or what happens when you compress data through into Mr. SID or JPEG 2000. What are the consequences of compressing or overly compressing the data and coming back? What happens? What's useful? What happens to geodatabases or GeoJSON files if you limit precision and export data? How do you recover the original data? Is it possible? And what should you expect to be a problem? Working with tabular data, such as commas separated by value or tabs separated by value, JSON files, Excel, MDF, DBF, what kind of problems you can have and what kinds of data works well. So we're going to bounce back through a few. GeoJSON in the spatial and GML in the spatial are the least compact format. And something like a file geodatabase or a GeoPackage might be the smallest, depending on a few issues. If you're looking at tabular data and you're coming from CSV or TSV data into ArcInfo or sometimes into QGIS, they'll have a hard time recognizing numbers to be actual number columns, and so you'll have to sometimes do some post-import conversion to make data usable. JSON is very good about allowing you to declare data as being text or numeric. So it's very good in that regard, but it is not a very compressed format. And if you had millions and millions of records, GeoJSON might not be the best way to go. You should have a sense of those different pieces. Things like NoSQL variants for geospatial data, CouchDB, should at least know that they exist and that there are people who are using graph databases with geospatial information, NoSQL, Bigtable, Mongo, a number of these less common geospatial desktop formats that people are doing some big work with. You should know about them even if you don't know all of the idiosyncrasies of how to move data in and out of them. You should know about field type. Should know the difference between character formats, text, string, and varchar. When are they just jargon terms for the same thing, and when are they different? If you are importing a UTF-16 formatted text string into something that expects ASCII or UTF-8, what would happen? If you are working with integers, how likely are you to have numeric overflow, and what are the consequences of that? How do you convert from Unix time to JavaScript to ISO 8601? And what data formats you provide ways to encode that information into the data? And you should know what can go into a blob. Even in a DBF file, there's a concept of a blob. Can you store pictures in it? Can you store movies? Can you store PDFs in them? Can you store geometries in them? What types of formats can hold what kinds of information, and which ones are available in which data sources? On the UTF-16 versus UTF-8 or ASCII, if you've ever read a data file and it has all of the letters interleaved with what appear to be blanks, that's a really good indicator that you have read a UTF-16 file as if it was a UTF-8 file instead. And so you see this space gapping. You should have knowledge of those sorts of data conversion issues so that you're making good choices. What happens if you load ASCII data into UTF without converting it? Do you end up with unreadable data? What's the chance that you end up with unreadable data or even mangled data? If you've seen in Hurricane Irma, some of the Puerto Rico response, some of the Spanish accent characters have caused some systems to have significant issues. Nothing that cause people to be injured, but makes some of the labeling and titling of things less than optimal. Data relationships. Dr. Carlin was talking about joins, unions, merges. And when we're doing those, and we say things like merge all matches, or merge only merge one match, or if we say merge the left side only, what do these mean? What's a left outer join? What's a right outer join? What's an inner join? In addition to the links down below, there's a couple of additional links that are on Esri's website about these sorts of joins. If you're starting to use Esri's ArcGIS Pro, you'll see more and more of these terms of outer and inner joins. So from this first block where we're matching, and we only have a one-to-one, if we spatially join those two data, the table with apples matches the table with an entry in apples, and oranges matches oranges. And because mangoes does not match papaya, that one isn't in the output set. Whereas if I'm doing, and if I have set that up to be only that sort of match, then I have a one-to-one relationship. But if entities can occur in the table multiple instances, like the second block where I have apples in twice, then we get 4 apples out because the first apples in the left table matches the first and the last apples, and the last apples in the left matches the first and the last apples on the right. So we end up with this inflation of data. So if you weren't careful to make sure that you knew whether or not your input data was one-to-one or one-to-many, you might get statistics where you count, well, we've got 1 apple in the top example, and in the bottom you might report, well, we've got 4 apples, when you really only have 1 instance of apples and you really only had 2 apples on either side. So you need to understand the consequences and to some degree the ways that that's done. So inner joins are the first example where we're only looking at the mapped together in a single connection. In the bottom, that's also an inner join, and it's an unconstrained inner join without limiting to the number of connections. An outer join is, let's see that. Oops. An outer join occurs where if we were outer joining the mangoes table, the table containing mangoes, with the table containing papaya, if we were doing a left outer join, then the mangoes would, because it's in the left table, would be in the output. And if we did a right outer join, papaya would be in the output set. And if we did a full outer join, both mangoes and papaya would be in the output set. Some of this language comes from the database and statistics world, and sometimes the Esri jargon is a little bit different. So be aware of that, but also be aware that that questions might not necessarily use only the Esri jargon when describing these problems. So having a complete understanding of the language being used can help you avoid some tricky situations on the exam. So there are issues with converting between time. And I have seen and do regularly see people when looking at time, when you, for instance, when you talk to an Esri REST service, it records time in milliseconds since January 1, 1970. That is the Unix epoch. And all computer systems only keep time as plus or minus time from that exact point in time, which is arbitrarily 0. When we're converting between time, does our software allow us to treat our time object as an object like Python does and convert it to string or integer very easily? Is our time based on an integer value, and do we need to convert it to a floating point based value? And is it a character string like ISO 8601 format? And how do you, and what facilities does the software you have allow you to go back and forth between them? If you were looking at Microsoft SQL Server, it uses the same format that Esri uses. It's also the format that JavaScript uses. Python's format is floating point based, but still based on the same point of 0, but it's in seconds. And so milliseconds are encoded as floating point after the last whole second. We should be able to do simple things like move between degrees, minutes, seconds, or in the case where Al was showing us the National Geodetic Survey, they were describing that as hours, and that decimal degrees and hours are the same description for the same information. We should have an idea of whether or not we're using a WKB and what that is, and a WKT. Both of those are encodings used within ISO standards to represent geography. We're using the U.S. National Grid as our geography. What's the difference between geography and geometry? And how do we convert between the two, in addition to converting between datums or other projective information? Should have a knowledge of what's necessary to go back and forth between these things. If you haven't used it yet, there is a format for GeoPackage called Spatial Light, which has, as part of and it is a ISO standard. It's also a US military standard. It's also an OGC standard. And Esri supports it in ArcMap and in ArcPro. You should know how to bring data into databases when they're encoded as WKT or WKB, or bring them back out again. When talking about data quality, accuracy, resolution, and fitness for use, the gold standard that we currently have is the national standard for spatial data accuracy. And it's probably, if you download it, I think it's a 30-page PDF, including a number of appendices. But there is at the back of that a procedural guideline, step-by-step guideline, that shows you how to measure the spatial accuracy of any data set. And you should be able to follow that and know what the standard is and means. But it's very important to know just what those general steps are. The concept of a higher order data set is important when measuring accuracy. When you're measuring accuracy we always have to have some measure, some base point milestone to measure against to know how different we are from that other source. So if I have a higher order raster that has larger cells, so it's less granular, but the position of the cells is more accurate, and the size of the cells didn't have a weight on measurement of features, then the raster with larger cells could be a higher order and more accurate, even though it was less granular. You should know that a more complete data source, if I have a list of all of the addresses in an area, and I have a list of most of the addresses in an area, or some of the addresses, which one is a higher order data set when comparing tabular data. Within the NSSDA, within a number of different spatial accuracy standards, they have normative language. I have two examples here for accuracy reporting that allow you to write a very particular and constrained phrase that someone else, when reading that, would know exactly what you meant and exactly what steps you took to achieve that resulting report. And you should know a few of them. I would definitely know the NSSDA, and there is another one with an ISO standard. I'll make sure I get you a link later. And where they have language that is constrained, use that language, especially in your metadata, so that others can understand the steps you took and the exact meaning of what it is you're depicting. You should know what happens when you mix data of different accuracy. If I did a raster masking of vector data, and the raster data had a horizontal error, an E95 of 10 feet, and the vector data had an E95 of 5 feet, and I mixed them together, to what degree have I, in what way have I hurt the resulting information that I'm provided, and know my error reporting samples so that I'm able to report that correctly without causing confusion. So in the lower right corner, we have a confusion matrix. You may also know it as an error matrix. It lists as a crosswalk the output of a sampling system and the actual true measurements of a sampling system. You may see it as raw counts like you do here. You may see it as percentage ratios, and that tells you how accurate a process is when looking at it. You use this sort of matrix when you're looking at attributes. How often is something misclassified? Generally, you don't use this to say whether or not something is in the wrong spot. So we're looking at horizontal accuracy or vertical accuracy. You give that as an E95 or an E85, some other error ratio, and that when looking at attributes, you end up reporting them this way. And you will see this a lot with computer vision and raster processing. You'll see this with land use, land classification, automatic detection of features. We'll see those sorts of things appear here. So we have some exam questions. And we'll just go on through with them. So when we're looking at defined parameter filtering based on specific content in a field, refers to which. So we're talking about content in a field, and generally means a field other than the geography or the geometry column. So the only thing left would be the attribute query, whereas spatial would be related to the geometry, location. I don't find good use of this term in any source I can find, but it seems to appear to relate to some sort of gazetteer relationship. And cartographic query, I have no idea what they mean there. So you should know, say, for not just shapefiles, but for shapefiles, what are the three main components that you have to have? There may be additional components of your shapefiles. And this would be number B, the SHP, the SHX, and the DBF. And you should know that the SBN and the SBX go together, and they are the spatial index. And you should know the PRJ is the projection, and the shp.xml file is the metadata, and the DBF is the attribute file. So in calculations, which field type cannot have numerical calculations performed on them? So we have a mathematical type of integer, a mathematical type of floating, and character. You can't compute the average of a character field. But had they said the word mode, which occurs most often, certainly you can measure the mode of a series of character fields using them as classifications. So that might be a tricky thing you'd want to watch out for, that it's mathematical operations and not computations at all or statistics at all. So when looking at converting between degrees, minutes, seconds of latitude in the northern hemisphere to decimal degrees, what steps should you take? So do we add them together and divide by 3,600, which would be 60 times 60 seconds times 60 minutes to get to hours? Should we subtract? So the number D is the correct method here. And it should be something that gets ingrained into you pretty quickly. If you are working in implicitly west longitudes, without the minus sign, you need to re-add that to all three of the components before you come back and work with them. If converting from degrees, minutes, sections in the southern hemisphere, what would you do? And that would be, you would use a -1 on the latitude instead of a +1. So you'd multiply the answer times -1. So in this step, how would you determine the horizontal accuracy of a already orthorectified aerial image? The first one is not true, because when looking at the horizontal accuracy, and this is buried in the NSSDA, the E95 is based on the root mean square of the distance between points in each of the photographs. So number 1 isn't correct because it just says that things must match, but it doesn't say how bad they are when they don't match. And in general, they won't match exactly all the time anyway, so that would lead you astray. Comparing points of an orthorectified image to GIS layers doesn't tell you how to compute the accuracy, it just says how to compare them. And it doesn't allow you to come to a measurement of accuracy. And the last one was just funny. Okay, and So what was the statistical method you would use to determine an attribute, land classification accuracy? So when you're looking for attribute accuracy, horizontal position, first one doesn't mean anything. The statistical error of sliver polygons is again a positional measurement, so that would be the horizontal accuracy, not the attribute accuracy. The next one, a confusion matrix, tells you how often you're right and often you're wrong within a subset of the samples of the data. And that's the correct answer for the set. So with that, finish the session. Any questions?
Wendy, do we have any questions from the chat room?
Does not look like we do. I've just asked everybody. I said, any questions for Carl? He's the data king, and they agree.
That he is. Makes my brain hurt. I agree. I feel enlightened every time I'm in the same room with Carl. I'm sure you all understand why now.
So there was a bunch of questions about programming languages, and I don't know what's on the exact questions you'll encounter on your tests, but you certainly should know which programming languages you're looking at and which sorts of programming languages are good for different sorts of queries. But I wouldn't get into the exact semantics to say you have to be an ACE programmer to be able to pass questions on the GISP exam.
Carl, would you say, this is just an opinion question, I'm sure, but a lot of people would say that a GIS analyst of today really does need to have some programming background, which is a bit of a challenge for people that have been in the field for a lot of years. Would you suggest that to be successful on this exam, you do have to have a fairly reasonable familiarity with at least the fundamentals of programming?
So I've been listening very carefully to what the GIS CI exam people say. And they say they're like the technology is leading, the exam is never going to be on cutting edge. But as things get more and more common, they're more and more likely to appear on the exam. So going forward, if you don't know the difference between R and Python and SQL, I think you might be at a disadvantage. Now, you can do all three of those using your Arc Pro. Right. There is an interface to R from Arc, and there are wonderful examples. If you wanted to get a better statistical background, you might look at something like Kaggle.com for data science. Data science and GIS science are not that far apart in a lot of ways, and it's useful to be able to use it. And Kaggle will handhold you through simple data science questions.
Great answer. Well, if anyone else has any questions, then please put those in the chat room. Carl, I don't know, will you be able to hang out for our last half hour?
Yes.
Perfect. So throw your questions for Carl in the chat room. I certainly encourage you to listen carefully to what our final presenter of the afternoon, Lauren, will have to share as well. This is a truly international collaboration. I didn't share this with you, but we have presenters today that are coast to coast and not just in this country. Our final presenter is actually coming to us from Edmonton. So Carl, you have stopped sharing. And Lauren, if you would be so kind as to share your screen, we'll start the next and final presentation in about 2 minutes.
Oh, thanks, Mickey. My name is Lauren Dimitrick. I work with the City of Edmonton in the as part of the GIS analytics team. Previous to that, I've worked both private sector with the Alberta provincial government. I've spent quite a number of years working with ESRI Canada and also with a pipeline company. as it's already been mentioned, I'm based out of Edmonton, Alberta, Canada. I'd like to say I'm enjoying the nice weather, but we're hovering at about -10 degrees below centigrade for the next few days here. Winter does not seem to want to give us a bit of a break here, so I'm jealous of all you people that are keeping warm south of the border. Throughout my career, I've really spent a lot of time working both on the desktop side and on the back-end server side of things there. So I've spent a lot of time working with databases in the ESRI environment, also with the internet side of things with ArcGIS server, etc. And I've kind of dabbled in a lot of different areas, but the data side of things here is something I've had a chance to work on in quite a number of different ways here, and also in terms of data modeling. So we'll just get right into it here. As soon as I get my thing figured out. There we go. Okay, I'm going to be covering off the GIS design aspects and data modeling as listed in the unofficial study guide from October 2017. As you can see that this is covering off about 29% of the exam, and I've got quite a few different areas to go over here. So it's going to be through a lot of content. Inside of the guide, you'll find that there are a lot of resource links for each of the knowledge areas, and the presentation here, I've got links into the study guide and other useful areas at the end of the presentation. So we'll be covering, as you can see, quite a different number of topics here, and I'm probably not going to have time to get into a lot of detail on each of them, but just want to give you an idea in terms of some of the knowledge or some of the things that you should know for the actual knowledge areas, so that you're able to look up that information and have a successful writing of the exam. So we're going to be going everything from really general things that are associated with relational databases to things that are associated with hardware and the various data models associated with geographic information systems. I'm going to try and keep this as vendor neutral as possible, but keep in mind I worked with ESRI for about 15 years, so I'm still a little bit on the bias side. So, oh yeah, and the other thing I want to mention too is that some of the stuff I'm covering ties back into what Carl was talking about in the previous set of slides there. So there is a little bit of crossover, and I think that hopefully you'll see where the two areas kind of supplement each other or complement each other in terms of the knowledge here. Now, there was a question in the chat room about which programming language is a good one to know for the various data types, and this ties into data exchange procedures. So understanding what the various file formats are, what are the various file compatibility types in between the different types of software, looking at how projection, generalization, these other kinds of things might affect your data. I think Carl kind of was talking about that, like say with time formats and things like that. Now, some of the more common tools that you're going to find for working with data exchange are going to be things like the feature manipulation engine from Safe Software. And that will probably get you back and forth between most of the data types that you will encounter in your career. Python is another language that has got lots of tools that are available, both open source and proprietary, for converting in between the various types of data. I think the other thing about data exchange here is that you also need to understand how you're going to be moving your data. So is it going through FTP? Are you using web services? Is there a particular API that you're going to have to use for exchanging your data? You might be using SneakerNet. The other things are also understanding what types of files are commonly used for exchanging spatial data. So you'll find that shape files, KML, things like that tend to be used more often for migrating or moving data back and forth in between the various systems. So you really want to understand what all these different methods are and the tools that are available for you in order to work with them, and also have an understanding of for a particular software product what the actual default file format is for that software. So we tend to think of, on the ESRI side of things, there like the shape file. Maybe with AutoCAD, we're looking at a DWG or maybe a DXF file. So I want to understand that. Security restrictions on data. So what we're really concerned about in this area is who owns the data and what kind of privileges is a user allowed to have in terms of working with this data. So this example here is showing how security might be planned for use of data on ArcGIS Online. And we can see that we have a bunch of default roles. So we have users, viewers, publishers, administrators. And for each of those roles, we provide different types of privileges on the data. So for someone who's just viewing the data, we're only going to allow them to have view privilege. They're not going to be able to create, update, or delete data. Where someone who's an administrator is obviously going to have full-blown access into everything. You want to know how you go about and create these groups and roles for your data. So you want to understand how that is going to work not only for, say, something like ArcGIS Online, but also within the various database management systems that you might run across. You have to understand how users are authenticated. So are they being authenticated using the operating system? Are you using database authentication? And there's a whole bunch of different authentication things that are happening out there. OAuth 2, we've got SAML, a variety of ways that this can all be managed. So you want to be able to understand, depending on what type of role a user has, what kind of access do they require on their data, and they shouldn't have any more than what they actually need for accessing their data. Database administration. So one of the big things now is the fact that we're storing a lot of GIS data inside of database management systems. And to work with your DBAs, your database administrators, you should have some basic knowledge of the tasks that are associated with database administration. So how do you go through and manage things like backing up and recovering data? How does the database security work? How much storage space on disk are you going to require for your data? What tools are available for monitoring performance of your database? How do you tune that database performance? And also troubleshooting, finding problems and fixing them. So if you're in a smaller organization, you have the potential that you're going to have to be not only the GIS expert, but you might have to be the database administrator for that GIS data. So when you go in and you start looking at the at your database administration, the knowledge that you're going to need to have will include all of these things in terms of the data types, various types of security, your storage, the understanding of the actual database architecture itself, and things like that are going to come into play. The next area for this knowledge portion here is understanding of systems architecture and design. So you want to understand the various phases that are involved with designing an enterprise system. So how do you gather your business needs, understanding the applications, who the users are, what kind of data resources they have, understand you'll need to understand the various types of processes that happen at each of the phases of implementing a system architecture and design, and be able to answer questions such as, how do you determine the size of a system? How do you go about and do your capacity planning? The network storage. What kinds of what are the various types of storage architectures that are available? So, that's very important when you're coming up to designing of the GIS system these days, especially now that we're moving more into an enterprise environment within larger organizations. We have to know how to plan these things out so that everything is talking nicely and data is flowing through quite well, which kind of ties into the next slide here, where we want to understand what the enterprise environment is. So these days, there is a whole ton of technology that is involved with an enterprise environment. So you want to know, what a local area network is, what a wide area network is, the internet. What are the differences in between those? When we start looking at things like servers, are you dealing with a database server versus a web server? Storage again, so talking with and understanding how storage area networks work. Are you working with desktop clients versus terminal server clients in there? And understand how all of these components integrate and work together. So if you've got, say for example in the slide here, and you've got a maintenance database versus a publication database. So what are the differences in between those two? And maybe why would you use a maintenance database versus a publishing database? So where is the proper place to use these types of things there? Are you working in a disconnected or a partially connected network environment? Now, I'm going to be talking about schemas a couple of times here, and there's the first one I want to talk about are things such as the actual database schema itself. So you'll need to understand inside of a database environment what the actual schema is, what are the tables, the views, have you got any stored procedures, those kinds of things in there. The actual data dictionary, so how do we inform the users as to what we actually have inside of the database. So this first picture on the slide here is showing an example of a geodatabase schema. So we've gone in, we've got a landscape feature class in there, or feature data set, and then we have separate feature classes that are underneath of that, and then the various subtypes that are associated with that. Along with that, you're probably going to want to understand domains. Now, this is looking at domain codes as they are inside of an ESRI geodatabase. And so you'll need to know what is the difference between a coded value domain versus a range domain, and how do the two of them work, and what are the proper situations for using them. And so here, in this example, we're looking at a coded value domain inside of a geodatabase in the ESRI environment. Now, you may apply domains differently using different databases or different types of software in there. So make sure you understand how those works in a couple of different environments. The next area is how we manage our digital files. So how do you actually go through and share data within your environment? How are the files organized and managed? Are you looking at a particular type of structure inside of your file directory? What types of files are being used? Understand how your data is backed up. So are you backing it up in a database, or are you backing it up from the file system onto a tape drive? the example on the slide here is showing us the various types of files that we might find as displayed inside of a catalog application such as Art Catalog. So here we can see that we've got some shape files, we got some text files, dbase files, shape files in there. Other things that you'll need to know for your digital file management is how is the data created and edited. So what software packages is being used to create the data and or edit that data? Are you working in an environment where only a single editor can access the file at any one point in time? Or is it an environment where you have multiple or multi-user editing? The other thing to keep in mind is that files can also be stored locally inside of a database, or we can have cloud-based storage. So that is also going to have an effect on how you access and manage your files. So having something local on your hard drive is quite a bit different than accessing it through something, say, like Dropbox or Google Drive. The other one is an understanding of what metadata is, how it's managed, what standards are in place for metadata. You'll often hear the ISO 19113, I think. I know I may have forgotten that one, but there's a whole range of metadata standards that are out there, and you need to understand what those standards are, what they require. You might also probably want to take a look at how edits are managed using a versioning system. And that is something that is also going to have an effect on how, whether you're working in a single versus a multi-user editing environment. And here we've got an example of a geodatabase in there. And looking at an example slide here of a editing environment where we've got multiple users that are editing on 2 different projects, and how that looks inside of the database for multi-user editing using a versioned environment, so keeping track of the state IDs inside of the database. Database design. So as part of understanding data management is understanding the processes and steps that are involved with database design. So you want to understand what components are part of the requirements analysis, your actual database design. So what are the differences between a logical model, a physical model, and a conceptual model, how you go about and implement that. So looking at, say, the data conversion and loading steps in there, how are you going to test your data, go through and do your quality assurance on the data. Try and get the data in as good as quality as you can get it as you're moving it into the database in there, and that this is not just a straight flow through process here. That database design is often going to be very iterative. So you're going to go through each of these steps multiple times. Another important thing that it's going to be covered in the exam here is the actual structure of a database. So this is kind of generic, but the components in here should be common across most relational database management environments in here. So, this is going to tie back into your physical data model there. You need to know where and how these things are created and managed inside of the database environment, and what are the various components. So what's the difference between a table and a view? What is an index? Other components that you could have in here are backup and log files, possibly the memory structures of the database, things such as procedures, triggers, physical servers, and understanding what each one of these components do and or provide to the database environment. The next thing we want to touch on is geospatial data structure. So this is a little bit different than the schema of the database, in that what we're dealing with here is the actual topological structure of our data. And this is important because it tells us how we maintain the spatial integrity of our data. And I'll talk a little bit more about geospatial data models in a later slide here. So the first example on a slide here are the various types of topologies that are available, and this is these are the some of the ones that are inside of ESRI topology rules. You know, so what is an arc node topology versus a region topology? Point events, route topologies. So there's a whole bunch of different topologies, and what we usually happen there in this case is we end up with a bunch of rules that help us define that topological structure inside of our database. So for example, the first one there, rule number 9, between two line feature classes, is we can have a rule that says the lines must not overlap with each other. So that could be within a single feature class, it could be between multiple feature classes. We can have a rule that says for lines and polygons that a line must be covered by a polygon boundary. Again, could be between one feature class or multiple feature classes. So you'll want to understand, or you want to go through the topology rules there and have a handle on those ones and how they're applied. Once again, taking a look at our overall structure, is have a knowledge of the differences between desktop, server, enterprise, and hosted applications. GIS can be deployed on many different platforms for the software, and so you'll need to know, what are the differences when you're implementing this, whether it's the software on a desktop, if you're working with hosted services such as software as a service or infrastructure as a service. What are the different deployment patterns? So if you've got, when you're dealing, say, with software as a service, there's all kinds of different deployment patterns and best practices in there. Also understand or learn about what are the various advantages or shortcomings of the different methods of the implementation. So the methods are not one size fits all, and you have to know when is the right time to apply or deploy the right solution in terms of getting your software out to your users. And hardware capability and software capabilities. So given the fact that GIS will run on just about anything these days, I haven't seen a watch-based application yet, but I'm sure that's coming. You need to know where your software is going to be deployed and what kind of hardware. So understanding what kind of software runs on what kind of hardware. What are the operating system dependencies in there? Are there particular database dependencies that you need to be aware of? Understand what the different components are for your system infrastructure, and also what's the difference between real hardware and virtualized hardware, which is, of course, a big thing now that quite a bit of the server side of things is now running on virtual machines. So definitely something you're going to want to spend some time with and taking a look at the information on that. Now, the data models here, what you need to know for the exam is what are the various types of ways that we model data inside of the GIS world. So the two most obvious, as I've got shown here, are the vector and the raster data model. So what's the difference, say, between a point and a line and area representation if you're using a vector versus a raster base in there? How do you best represent a feature? Is something a point? Is it a line? The other types of data models that you'll want to get brushed up on include things such as triangular irregular networks, network models, so geometric networks versus, say, road networks, object-oriented model in there, and what are the disadvantages or advantages of the ways of representing the various types of spatial data. So, you know, there are times when it may make more sense to represent something as a raster than it will as a vector. So just a couple of quick exam questions here. So the first one here ties back into our data file formats, and which of the following formats is most likely to represent a file exported from AutoCAD Autodesk? And in this case, they want the best response. Anyone in the chat window want to take a stab at that? Is it a shape file, a DXF file, a text file, or an LAS? Oh, there we go. Everyone's got that one right. It's a DXF file. And the next one here, which is following is not a true relational database? Choose the best answer. And once again, if you just want to enter the chat window there. Okay, that one's almost a gimme. If anyone thinks Access is a real relational database, then there you go. Okay, so this is the links here, and hopefully those will come across in the PDF there. But definitely the exam preparation. All these ones in here are the ones that I went to in order to get some of the information in here. And there's lots of good stuff out there. And the links that are provided in the what did I say, in the knowledge area earlier in the unofficial study guide from October 2017 have got a ton of links that will get you brushed up on the knowledge that you need for this particular section of the exam. And with that, I think I even have a couple of minutes for questions.
I do believe you do, and thank you, Lauren. This has been really good. Wendy, I've seen a lot of chatter in the chat room. Is there anything that we want to present to Lauren before we wrap up?
Yep. Looks like just a lot of sharing of information and links and answering Lauren's questions. So it doesn't look like we have any outstanding questions at this point.
All right, fantastic. Well, we are almost exactly.
Oh, wait.
Yeah, please.
We just got one. Somebody
right.
wants to know more about the triangular and object-oriented models.
Yes, so a triangular irregular network is often used for terrain modeling, and if you look at it, the data looks a lot like a little triangles that join together and actually create a surface. So it's one of the ways that we use for representing a surface inside of a GIS. The object-oriented model is looking more at how things are actually stored inside of the database. So we can think of a feature as a particular object, and then we have the various properties about that are stored inside of the database. That's just straight off the top of my head there with that one.
Great answer to me. All right. Well, I will invite anyone that has any questions after the fact to email those to the presenters. Again, your information, all of the information for the presenters is going to be posted online, along with the other stuff that we've talked about. Wendy, we've got about a minute and a half, and I know there's a lot of really neat things coming up in our world in ERISA. Do you want to share a couple of those with everybody?
I can very quickly, but if 15 seconds of that can answer Catherine Wright's question. She has asked if there, whoops, where'd it go? Asked if there were particular languages better to extract particular data types.
Lauren, you want to field that?
Yeah, if you're looking at something that's inside of a database, probably the first place you're going to go to is going to be SQL. Probably, I would say my go-to personally for the past few years has been Python. And lately, I've really been enamored with Safe Software's FME, which is not really so much as a language, but as connect the dots in between various things there, which doesn't really even require any programming. I think that you'll find that each software package usually has tools built for extraction into a variety of different formats. So you may not have to do a lot of programming. It may be more scripting. Say, for example, if you're working in ArcGIS, you would write a Python script that would then call something that would say convert from a geodatabase into a shapefile or into a DXF file. So, probably that's where I would be looking at it that way, as opposed to saying, well, you really need to be using C# or Pascal or I don't know, Perl for extracting languages or for extracting. But I think Carl's point earlier about being able to look at a language and maybe have a basic understanding of what programming language it is would probably be quite helpful.
Excellent. So I will say a few words about upcoming ERISA activities. Right around the corner, starting Monday actually, in Columbus, Ohio, is our GIS Leadership Academy. It's a fantastic opportunity to dive deep into topics like the difference between leadership and management, strategic planning, communicating the value of your GIS, putting a team together, dealing with change on the job, that sort of thing. And it's all done with a GIS twist to it. All of the instructors are GIS professionals. All of the folks attending are at various levels of management within their organization. It's one of the programs we like to toot our horns most about. So we have the one next week in Columbus, Ohio, and another one at the end of July in Salt Lake City. We're trying to present it twice a year. We try to limit it to 50 people at each offering. So if one looks interesting to you in the future, just jump on that. We also have GIS Pro, which is combined with Cal GIS this year. We'll be in Palm Springs, California, October 9th through the 12th. The conference program is nearly put together. It's taken us a little longer this time because we had about 3 times the normal number of abstract submissions that we normally get. So I think a lot of people want to go to Palm Springs. We're almost finished putting that program together, as I mentioned, and that should be out probably by mid-April. So I'll be working on that next week. But get involved. We've got our young professionals group, the ERISA Vanguard Cabinet, that is incredibly active. And as I mentioned earlier, there were a few of our young professionals on this webinar yesterday and today. It's a great opportunity to dive deep into ERISA, meet some of your fellow peers, and start leading the organization. So I greatly encourage you to get involved, as Kevin's been mentioning throughout the program, and getting to work with you all closely in the future.
Well, thanks, Wendy, and thanks to all the presenters today, and to those of you who took such a significant amount of time out of your schedule over the last couple of days. We hope it was very much time well spent. So I'm going to go ahead and end the meeting now, and if anyone does have any follow-up questions, then feel free to reach out to any of the presenters individually or to ERISA leadership. We are there for you. Thanks, everyone.